Now, for problem number 8, we have two 40-foot long wires made of differing materials and that are supported from the ceiling of a testing lab. Wire 1 is made of material H and has a diameter of 3/8 of an inch. Wire 2 is made of material K and has a diameter of 3/16 of an inch. When a load of 225 pounds is applied to its lower end, wire 1 stretches 0.1 inches. When the same load is applied to the end of wire 2 stretches 0.25 inches. So let's compare materials H and K. First, we're asked which material has the greater modulus of elasticity, and then second, which is the stiffer material. So I think it would be beneficial to start with the sketch. So let's draw our anchor point across the ceiling. We have two wires suspended here. We have wire 1, which is material H. Yeah. And we have wire 2, which is material K. Wire 1 has a diameter of 3/8 of an inch, and wire 2 has a diameter of 3/16. Both of the wires are 40 feet long, and both of the wires are loaded with 225 pounds of force. So again, we're given the amount of stretch on each of these. The elongation here for wire 1 is 0.1, and the elongation for wire 2 is 0.25. So because the two wires are not the same diameter, we can't just eyeball this thing. Even though they're loaded with the same amount of force, and even though they're the same length, because we're not looking at the same size wire, it doesn't really tell us the whole picture that wire 2 is stretching more. Wire 2 could be stretching more just because its diameter is smaller. But we'll need to do the math to find out. So we're going to find the modulus of elasticity of both of these things and compare them to figure out which is the stiffer material. So what do we know? We know the diameter of wire 1, 3/8 of an inch, 0.375. We know the diameter of wire 2, 3/16 of an inch, 0.1875. We know the elongation of wire 1 to be 0.1 inches, and we know the elongation of wire 2 to be 0.25 inches. We know the applied force in both situations to be 225 pounds, and we know the length to be 40 feet or 480 inches. Now, what we don't know is our modulus of elasticity. We don't know the cross-sectional areas, and we don't know the strain. And to find our way to the modulus of elasticity, we're going to want to understand both the stress and the strain. To understand the stress, we're going to need to work with force and area. So let's see. We'll need to get to the cross-sectional area. So these are wires. They're round, pi r squared. We'll need to find the strain using the elongations and original lengths that we know. We'll need to find the stress using the force we know and the area that we're going to find, and we'll use those together to find the modulus of elasticity using stress over strain. So I'll divide this right down the middle, and we will work out wire 1 on one side and wire 2 on the other. Our area for wire 1 equals pi r squared, and our radius is 0.1875 for this one, again half of 3/8, which works out to 0.1104, and so on. I'm just shortening that. That's what that underline means. Square inches. Our area for wire 2, again, pi r squared, where r equals 0.09375. And that is going to work out to 0.0276 square inches. Next, we can use that area to figure out the stress for wire 1. Force divided by area, 225 pounds, divided by 0.1104 square inches, using the unrounded area here for the most accurate result. And we get 2,040 pounds per square inch. For wire 2, our formula is going to start the same way. Stress equals force divided by area. And our force is the same, 225 pounds. We're just dividing by the different surface area, which comes out to 0.0276, and that's actually longer than that. And when we crunch those numbers, our stress for wire 2 comes out to 8,152.2 pounds per square inch. Looking at our strain for wire 1, our strain is going to be equal to 0.1 inches of elongation over 40 feet times 12 inches, which works out to 480 inches. Or when we crunch those numbers, 0.00021 inches per inch. And our strain for wire 2, same formula, elongation over original length. This time we have 0.25 inches of elongation over 480 inches of original length. And our strain comes out to 0.0005208 inches per inch. Finally, our modulus of elasticity for wire 1 is going to be equal to the stress over the strain, which is for wire 1, 2,038. And again, here I'm trying to use the unrounded number that I calculated up above. And our strain is the 0.00021. So our modulus of elasticity then works out to 9,800,000 pounds per square inch. And I've rounded that to the 100,000s place. It's not actually one of my required answers here. So where I round it is less important than comparing the modulus of elasticity of these two materials. So let's repeat the process for wire 2. Stress over strain. This time it's our 8,152 pounds per square inch stress over 0.0005208 inches per inch of strain. And our modulus of elasticity this time comes out to about 16 million pounds per square inch. So rounding this number all the way at the 100,000s place really didn't make a difference in which material had the greater modulus of elasticity, far greater on wire 2. So back to the questions. The questions were, which material has the greater modulus of elasticity? That was wire 2, material K. and part B, which is the stiffer material. The higher this number is, the higher the modulus of elasticity is, the stiffer the material. So again, wire 2 is the stiffer material.